Thank you.
Everyone, thank you for joining us today. Today I am going to be giving a talk on SYCL performance and portability. I am Kumudha Narasimhanm and I am a software engineer at Codeplay. This talk is going to be for 30 minutes. I'm going to be talking about the various performance aspects of SYCL and how the code can be portable. So if you have any questions, I'll take them at the end of the talk. So if you haven't heard about us, Codeplay is a company of 80 people. We are based in Edinburgh, Scotland. We actually design and develop heterogeneous solutions based on open standards such as HSA and SYCL. We develop compilers, runtimes, and other tools for different domains like automotive, vision, for different customers like ARM, Renesas, etc. So why is portability so important? So if we look at the way the processors have evolved, we first had single-core CPUs, then came the multi-core CPUs, where to get good performance, the most important thing was to parallelize your code and utilize all of the cores that are present in the system. Nowadays, along with multi-core CPUs, we also have system-on-chip processors, which are highly optimized cores for each class of algorithms, or for different data types, or for both algorithms and data types. So now is an amazing time for power processor architects who are coming up with these new innovations of architectures and accelerators. But for anybody who is trying to write code which is performant on all of these different classes of processors, it is going to be very hard. So what is the solution to coming up with performant code that works on all of these processors? One is to actually sit and hand code all of these, all the programs to work on each of the new processors. But by the time we have it working on one processor, there is already another one in the market, and then whatever we have written would become obsolete. So the most or the best solution would be to actually use tools or frameworks which help you write the software or the program in one format and then tune them for any new processors that come for getting better performance on them. So this is what we are going to discuss in the rest of this presentation. So yeah, the question is, how do we write programs, libraries, and tools which can be parallelized and optimized into different systems? So over here, in order to achieve this, we actually try to use this modern C++ concept called separation of concerns. We try to separate the problem into multiple different small problems and then try and deal with each of these small problems. So the different small problems that we have divided it into is what we want the software to do. The functionality of the software is divided from all the optimizations or the algorithms and everything else. That is the first division. The second stage is the algorithm that is used to calculate the answer. By dividing this, we can always replace different algorithms based on different processors. The third division is processor-specific optimizations. So what do we mean by processor-specific optimizations? If the processor has tensor cores, or if it has matrix multiplication units which have been designed to use very highly efficient MATML operations, then we can use that instead of actually using our own MATML operations. The fourth division is how the data is stored. So we have seen that the type of how the data is stored, or the format or the layout in which the data is stored, can also be one of the reasons in which the performance is affected of a particular software. So we actually divide the problem into smaller problems. Now that we have divided them, we can independently choose the algorithm, the optimization, which processor optimizations we need, or where we want the task to run on, and how we want to store the data. And since these concerns are separated, now the task of finding the fastest algorithm on a given processor is run all the different options you have and then try and see which is the fastest. So we break down the optimization problem into 3 stages. The first one is writing optimized algorithms for the particular problem, finding data structures and kernels which optimize the data, as well as finding schedules which actually improve the performance of the system. Next, we have to write software in such a way that each of these algorithms, data structures, kernels, and schedules can be switched depending on which processor we are using. And thirdly, we choose the best option for each of the problem we want to solve based on the processor or the hardware that we run on. So we saw the concept of how we can separate these concerns. So how do we put all of this into one component which can be actually used by a system? So we can write a cat-free written C++ library that can combine all of this with the user-written code. To achieve this across different data formats and algorithms and the processors using user customizations, we would need to have all of this inside one C++ compilation unit. This is called a C++ single source compilation, and it is crucial for supporting today's heterogeneous multi-core processors. So next we look at what are the libraries or the compilers which support the C++ single source compilations. So there are many C++ libraries like Cocos and Raja for high performance computing, which already have a support for this, Eigen, which is used in AI and robotics. Later in the slides, we are going to look at SYCL-BLAS and SYCL-DNN, which are libraries as a part of the SYCL ecosystem, which also support single source compilation. Many compilers also currently also support this. One of the main things is SYCL, which is an open industry standard for heterogeneous computing. There are many implementations of the SYCL standard like Compute CPP, DPC++, Tricycle, which are available. The latest C++ parallel STL compiler also supports single source compilation and many others. TensorFlow is one of the applications, which is an example of single source compilations. Many accelerators like NVIDIA GPUs, AMD GPUs, even specific architectures like Renesas ARCAR also support SYCL. To support all of these optimizations, we needed an industry standard for all of the heterogeneous applications on how they can provide performant code, which is also portable across processors that are already available, plus the processors which would be developed later in the years. So as a result of this, SYCL was introduced. SYCL was the result of the industry standardization effort, and it was led by Codeplay. So what is SYCL? SYCL is a royalty-free, vendor-neutral industry standard C++ for parallel software and accelerator processors. What do we mean is it's an open source standard which can be used by anyone, be it research, industry, anybody, to implement their own high-performant SYCL standard compilers. One of the main reasons for making this open and royalty-free was to encourage innovation and development in this area. What SYCL does is it takes the proven C++ performance ideas that we discussed and it supercharges them for the heterogeneous processing worlds. SYCL helps build a new C++ SYCL compiler for any of the processors that come into the market. It also helps build C++ libraries that can adapt to the performance requirements of different systems. SYCL also provides native compilation support for different processors in a single source file. This slide shows an example of a SYCL application. So the left side shows a CUDA example and the right side shows a SYCL example. So one of the first things that you can notice is in case of a CUDA example, we use the angular brackets to indicate where the kernel launch has to happen and where the computation has to move from the CPU to the GPU. If you look at the SYCL example, it is completely C++ code with just C++ formats and no extra syntax to show when the computation has to happen on the CPU or on the GPU. So how does SYCL decide when the computation or where the computation needs to happen? This is basically handled by the queue. The queue that is used over here has a function called submit, which accepts a lambda function. This lambda function is the operation that we need to be performed either on the accelerator or on the host processor. The type of queue we use to perform this lambda function decides where this operation is going to happen. So that means we can have different types of queues. We can have a queue for the CPU, we can have a queue for the GPU, we can even have queues for different types of GPUs. We can have a different queue for an Intel GPU versus a different queue for an NVIDIA GPU. Depending on the type of queue, the code can decide where this particular operation needs to be run. This slide also shows how the memory management happens in CUDA versus how it happens in SYCL. So the basics of CUDA is it does a CUDA malloc, a CUDA memcopy, where the data is moved from the host to the device. In case of SYCL, we use buffers. So buffers can have different scopes. The buffer can be either a global buffer, that means it can be used either on the host memory or on the device, or it can be just on the device. The scope of a buffer is within the example or is within a particular place where it is defined. So as soon as the buffer goes out of scope, it is destroyed. To every Lambda function or to every a command handler or the submit that we give to a particular queue, we pass the buffer, and we can use something called accessors to access the memory that we have on the device. So that is what is shown over here. We have an accessor called A, which can be used in different modes, either on the read mode or on the write mode, depending on what operation we want to perform on the data that is available in this buffer. The indexing is shown in the blocks that is represented in the blue, and the block size and the grid size calculations is shown in the block represented in the green. So as you can see, it simplifies the code. So the same code that we see over here can be run on the CPU, GPU, or even any processors or any of the chips that come up. So at Codeplay, we have our own implementation of SYCL called Compute CPP. Compute CPP works on top of OpenCL and Spearway, and it works on PowerVR, RCAR, which is from Renesas, ARM boards, Intel CPUs, Intel GPUs, as well as AMD GPUs. Codeplay released a free version of Compute CPP, the Community Edition, to help build out a SYCL ecosystem. Codeplay also provides training events at conferences to encourage people to learn SYCL, and it also provides a free set of open source learning materials called the SYCL Academy. So the initial versions of SYCL were built on top of OpenCL, and hence they were not supported on non-OpenCL backends, for example, CUDA. But with the introduction of the plugin interface, we can directly run SYCL programs on non-OpenCL backends as well. One example of this is the SYCL for CUDA, which was implemented on the Intel's TPC++ compiler. SYCL also supports interrupt task, and the interrupt task enables the support for calling native libraries in SYCL. So what we mean by this is any of the native libraries for a particular processor which has been already tuned or provided for a particular processor can be directly called from a SYCL program. One of the examples of this native library is shown in this box, where inside a SYCL program we are actually calling CUBLAS library function, CUBLAS SGEMM, which actually does matrix multiplication. All of the data which is passed to the CUBLAS function is created in the form of a buffer, and it is all passed as a part of this interrupt task which is available over here. So what is the advantage of having this facility in SYCL is that the scheduling of your call to the native library is handled by the SYCL dependency graph.
Live market.
Till now, we spoke about the portability aspect of SYCL, how we can write a single program and it can run on different OpenCL compliant processors, as well as non-OpenCL processors like CUDA GPUs. From here, I'm going to be presenting a few slides which represent independent SYCL benchmarking, which show the performance of SYCL compared to native either CPUs or CUDA GPUs. So the first one over here, the first two graphs, represents the Babel stream benchmark. The Babel stream benchmark is a benchmark used to measure the memory transfer rate to and from a capacity memory. This benchmark does not take into consideration the PCIe transfer time. The first graph actually shows the comparison on for EX, Ivy Bridge, KNL, and S9150 for different versions of HIP-SYCL compared with OpenCL, CUDA, OpenACC, as well as Cookhouse and Raja. The second graph actually shows the bandwidth for CUDA compared to HIP-SYCL. We can see in both the cases that SYCL performs either as good as or maybe a few within like 5% of the actual CUDA benchmark over here. The second or the third graph over here shows the performance of SYCL for multigrid methods. So multigrid methods are fast scalable numerical solvers for partial differential equations. This study was done by Frederick Alexander University. And it shows this SYCL code generation for multigrid methods. We can see that, so this shows the speed up, show the higher the better, and the x-axis shows the size of the multigrids. So we can see that TriSYCL and Compute CPP are two implementations of SYCL, but compared to CPUs, the performance obtained by SYCL is higher and much better. The next benchmarking we are going to be talking about is for reductions using SYCL. This was done by University of Dresden. The graph on the left side shows bandwidth on the y-axis and the different systems on the x-axis. The graph on the right side shows peak performance or the gigaflops on the y-axis and the size on the x-axis. This benchmarking was compared with was done on NVIDIA GPU K20, and it was the comparison is with the CUDA application. As you can see, the bandwidth is very similar to that of a native CUDA application, and so is the peak performance. It is within 5% or as good as a native CUDA application. The next benchmarking was done by Argonne National Labs. The used here was called XSBench. The x-axis represents the various benchmarks. The green tab represents the CUDA implementation of the benchmark. The blue bar represents the optimized CUDA implementation, and the orange bar represents the HIP-SYCL implementation of this. SYCL achieves equivalent performance to an optimized CUDA application on the V100 NVIDIA GPU. The next performance comparison is for the SYCL for CUDA implementation, which was done for the Intel's DPC++ compilers. As I mentioned previously, Codeplay contributed for the open source DPC++ compiler, which was created by Intel. Over here, we have used the Babel stream benchmark, which we discussed previously. The x-axis represents the different benchmarks. The y-axis represents the bandwidth, which means higher is better. The orange bars represents SYCL, the performance of SYCL, or the bandwidth obtained by SYCL for CUDA, which is the backend that we wrote for DPC++. The green axis represents the actual CUDA performance for each of these benchmarks, and the blue represents for using OpenCL on the NVIDIA GPUs. Again, as you can see, the SYCL for CUDA, even though this is just the initial numbers, is as good as native CUDA applications, or is within 5% of the performance. SYCL also comes with a complete ecosystem of libraries. The SYCL ecosystem is fast growing. It includes SYCL-BLAS, which is an open source BLAS library, which supports linear algebra operations. We will be talking about SYCL-BLAS and SYCL-DNN later in the slides. The other one is a SYCL-DNN, which is the open source deep neural network library. SYCL-ML supports classical machine learning algorithms. TensorFlow also has an open source SYCL backend. Argonne also has an open source SYCL backend. 1MKL is the Intel's open source SYCL MKL library, which also has a CUDA support CUDA backend support available. So what is SYCL-BLAS? SYCL-BLAS is an open source BLAS library, like we already mentioned. This is similar to C++ style NVIDIA's new CUDA-class. SYCL-BLAS was done in collaboration with University James Castellan. SYCL-BLAS supports Intel GPU, PowerR, ARCAR, AMD GPU, ARM Mali systems, Intel CPUs, and many other backends. The main optimization or the main advantage of SYCL-BLAS is it supports kernel fusion for high performance on complex algorithms. Thereby, it reduces the memory bandwidth that is being used. SYCL-BLAS also adapts to be optimal on different GPUs and AI processors by using C++ templates, which lets us use the same source code and get a better performance depending on which system we are using. It also adapts the algorithm based on the memory sizes as well as the types or the vector widths available from a given problem. It also adapts its algorithm based on the size and the shape of the input. So this is the performance numbers of SYCL-BLAS. This is shown for GEMM. We compared this on the Intel iGPU with the OpenCL-BLAS implementation. It shows gigaflops, and the x-axis shows the sizes of matrix used for performing the GEMM operation. This was optimized for a range of different shapes and sizes, and this is used in many of the deep learning libraries. As you can see, SYCL-BLAS performs much better than the OpenCL-BLAS implementation. SYCL-BLAS achieves really good performance on different processors by actually having hand-optimized libraries integrated for specific operations based on which processors it is doing. SYCL-BLAS also supports to tune parameters for algorithms per processor based on how much of on-chip local memory is available, what is the work size group, if double buffering is available or not, are there bank conflicts on the on-chip memory, what is the cache line size available. So basically there are many parameters that can be tuned to get better performance from the processor. So we also continuously run huge number of benchmarks with different optimization parameters. So basically SYCL-BLAS is the system which is available, which utilizes whatever concepts we spoke up until now. The framework allows you to actually switch between different algorithms or switch between different tile sizes based on what is supported best for the given processor that you are running on. This graph over here again shows the relative performance of SYCL-BLAS. It compares the SYCL-BLAS from Intel CPU versus Intel CPU SYCL-BLAS versus the OpenCL CPU. Again, Intel GPU OpenCL version as well as the Intel GPU SYCL-BLAS version. And you can see that consistently, no matter what, if we are running on the CPU or on the GPU, SYCL-BLAS performs better than the OpenCL-BLAS version. Another open source library as a part of the SYCL ecosystem is the SYCL-DNN. SYCL-DNN is, it adapts the algorithms according to the GPU or the DSPs or the FPGAs that we are using. It allows different accelerators to benefit from different algorithms based on the amount of memory that is available or on the shape of the convolution that they are using on the architectures. It also supports different types of convolution algorithms like direct, direct-tiled, IM2-call, Vinograd, and GEMM using matrix multiplications. SYCL-DNN also supports both training and inference. It supports 2D convolutions, pooling, 2 depth-wise convolutions, ReLU, tanh, and so on. You can actually visit this GitHub link if you want to know more about SYCL-DNN. In this slide, we try to understand how SYCL-DNN does auto-tuning per processor. The first 3 graphs represent different convolution algorithms. Convolution is one of the operations that is very commonly used in deep neural networks, and we can use different algorithms to represent this convolution operation. So in this case, we use 6 different convolution algorithms, including direct, Winograd, tiled, IM2-call, matrix multiplication, the different algorithms, and the commonly used convolution shapes, and then see how a particular processor responds to each of these convolution shapes and the algorithms. SYCL-DNN runs these algorithms for the different shapes of the convolutions, and it learns the best algorithm for each shape and size. After we know which is the best algorithm for a particular processor, then we can go one step ahead and run a range of different tile sizes and shapes on each of these algorithms that we have chosen for these processors, and we can learn the best tile sizes to extract more performance from the processor, even more than choosing the correct algorithm for that processor. By doing this, we can, for a given processor, determine which is the best algorithm and then go one step ahead and say which is the best tile size for running that particular algorithm. Okay, so we have been talking a lot about SYCL, how it is good, how it is portable, and how it is performant. So who is using SYCL today? So there are multiple implementations of SYCL, and one of the first implementations was Compute CPP, which was by Codeplay. It is a closed source implementation, but also a community edition is available to improve the SYCL ecosystem. The Compute CPP version supports OpenCL and Spear-based processors, which includes ARM GPUs, PowerVR GPUs, Intel GPUs, and many other CPUs. Another common implementation of SYCL is HipSYCL. This was an implementation by the Heidelberg University. This supports both NVIDIA and AMD GPUs, and it does not go through OpenCL backend. One of the other famous implementations of SYCL is the One API or the DPC++ implementation by Intel, and Codeplay has also contributed to the open source version of this DPC++ compiler. It is open source and it is under active development. It supports Intel GPUs, NVIDIA GPUs, as well as many Intel FPGAs. Another commonly used SYCL implementation is from Xilinx, and it is called TriSYCL, though it is not under completely active development right now. To learn more about what are the latest implementations of the SYCL or what are the new additions to the SYCL ecosystem, you can always check out sycl.tech. So to conclude, I would like to say that SYCL is an open source industry standard for heterogeneous computing. The standards are constantly being improved. It also has multiple vendor implementations, and these are actively being developed. SYCL is both portable and performant, and there is a rapidly growing ecosystem with One API, Compute CPP, SYCL-BLAS, SYCL-DNN, Argonne, and TensorFlow. So,
okay.
Yeah, that was my talk. So if you have any questions, I'll probably take them on the Slack channel.
Yeah, there are a few questions, and your colleagues from Codeplay answering them, but I can repeat the question. There was the point, what is the difference between the community edition and the professional edition?
Of Compute CPP?
Of Compute CPP, sorry, yeah.
I don't think there is much of a difference. The professional edition actually has a priority support, but yeah, example like profiling support is present in the professional edition. Even extraction of graphs, those are some of the examples that is present in the professional edition as compared to the community one.
Okay. Any other questions? Seems to be not the case. If you have questions, please use the Slack channel to communicate directly with Kumudha.